Hello everyone. So in the previous two videos, we discussed about the application of singular value decomposition in image compression, how it approximates an original image with um, different ranks. Followed by we discussed about the geometric interpretation of singular value decomposition, especially in Euclidean two-dimensional Euclidean space, right? How it transforms and geometrical shape in Euclidean shape. I hope those were the motivating examples. So in this video, yeah, there are some questions to think about and there are few questions to solve. So it's a kind of computational thing along with some interesting questions. So a sort of thing is that in linear algebra or in machine learning or in deep learning or usually in scientific field, we often deal with n-dimensional space. So not with 2 or 3, we usually go beyond 3, such as 100,000 or million. So in such a case, it is very difficult to visualize what is going on in the millionth dimension, right? So what do pioneers in this field exactly do in such a case? Okay, so when they see a vector or a matrix of dimension n greater than 3, how are they able to visualize? Okay, so let us see how do they do it. Okay, yeah, so to deal with the hyperplanes which are greater than 3-dimensional plane in a 14-dimensional space or power 14, so what they do, they simply visualize a 3D space and say 14 to yourself, right? So it's a quote. I don't know whether it is a quote or not. So it is said by none other than Geoff Hinton. Okay, I don't know whether you are aware of him. So he is a pioneer in deep learning and machine learning in general, or a pioneer in neural network architecture. So you just do a quick Wikipedia search, you will learn a lot about him. Okay, so that is the case. So we usually we try to understand the concepts in R2 and R3, and then if you are if you want to know how it behaves in R100, just say yourself, now I'm talking about in R100. Okay, so in line with this, so now the week 5 content is all about complex matrices. So the default question that rises to come that comes to our mind is that can we visualize a complex vector, right? So you just think about it. Is it possible to visualize a complex vectors like we do for real vectors, right? So in real case, suppose you are given with the vector x11, so you can take two real axes and then the orthogonal real axis, and then we simply plot the vector from the origin to the given point. That is what we do in real vector space, right? But what about the complex vector space? You just think about a bit, pause this video and think about the bit. So after thinking hard, is it really possible to visualize a complex vector? Let us start with visualizing a single complex number. Okay, say for example, if I have 1 plus I, which is a complex number, which is a number belongs to C, right? We do visualize a single complex number using two real axes. One we call it as a real part, and the orthogonal one we call it as an imaginary part. So if I have another complex number or an element from C2, okay, so the question is, if I have a vector x that comes from C2, say for example, if I add one more vector here instead of this question, if I put 1 minus I, now I have two elements from C, right? So how can I plot it? Think about it. Is it possible first the first hand? Obviously, it is not possible to visualize a vector from C2 or greater than C2, right? So the reason is, if I want to plot the other element, I need two more axes, right? So for a single complex number, we need two real axes, real and one is an imaginary. We need two axes. So if we want to plot a complex vector from C2, we need four axes. Okay, so which means we need 4 dimensions. So we can't do that even in 3 dimensions. So to visualize a vector from C2 or more than C2, so we need 4. So for C2, we need 4 dimensions. Okay. So in general, we can say C2 is equivalent to R4 and C3 is equivalent to R6, or for every complex number, we need two axes. We have to keep on adding two axes. Okay. So it's not possible to visualize a complex vector, but we don't care about it because we have an algebraic way of manipulating the vectors. So that is one skill that we should have. Okay. So apart from visualizing things, we should be comfortable with algebraically manipulating, okay, or logically manipulating all those vectors. Okay. Okay, so this is about a complex vector, but what about the complex matrices? Okay, so the next question would be, so far, even in singular value, in the application of singular value decomposition, we considered a matrix from real space. Okay, it's all the elements in the matrix were real numbers. But now, if we think about a complex matrices, the elements in the complex matrix is going to be sum of the elements, or all the elements is going to be complex number in general. So the immediate question that naturally comes to our mind is, do we really find application of complex matrices? Okay, so or is that just an other mathematical stuff that comes out of axioms, or it's just kind of pure math? Okay, those who don't care about the real world applications. Okay, so this is an obvious question which we need answer. So I can give you an answer. So you take a look at this matrix. Okay, so now this matrix is actually a complex matrix which contains, you see, some complex numbers. Of course, this is you can ask about the question real whether it is a symmetric matrix or a Hermitian matrix or Hermitian symmetric matrix. You can think talk about all properties or types of complex matrices. But the question is this all, whether the elements in this matrix are random? I just inserted all those elements because it should be a complex matrix, or it is coming from some concepts. Okay, so this matrix, which is a 4 by 4 matrix, comes from a transform. Okay, so a mathematical transform, which we call it as discrete Fourier transform. So the Fourier transform is one of the core transform that is applied in many domains. Okay, so you may not be aware of it, you need not to, by the way. So just to answer your question, if you have that, do complex matrices find any real world applications, I have to tell this one of the important transform. There are many complex matrices, but this one is extremely important one. So you should be very happy now, because you are not studying something abstract, something completely mathematical. So you are studying something that are applied in real world in many applications. So again, to give you some applications, I would say there are countless applications of this discrete Fourier transform, especially in signal processing domains, like the communication devices, the wireless communication, and your entire mobile phones, right? So the antennas in your mobile phone, all the signal communications is actually developed from discrete Fourier transform. Okay, they are somehow applying discrete Fourier transform uh, in your mobile devices. You can find all such components which makes use of this discrete Fourier transform, especially in speech processing, noise cancellation. Okay, so I can list out a lot, but anyhow, this is the subject of its own. So if you want to study about discrete Fourier transform and its applications, so we need another course, right? So that is signal processing, all such things, but we need not to go into that. But I just wanted to tell you that yes, there are applications of complex matrices in the real world. Okay, you just take it for granted, you trust me, that's all. Okay. Okay, now let us keep aside all these things and let us solve some problems um, from the week 5 contents. So the first problem and the one of the important problem is to computing the dot product or the inner product between two complex vectors. So here are two vectors x and y. You can read the elements in x and y. So we have to verify for this specific example whether the commutative property is applicable, okay, or these two vectors obey the commutative property, especially when I compute the dot product. So which means that I have to prove that, or I have to verify that. First I have to compute the inner product between x and y, and then I will just commutate y its place y dot x, and then see both of them gives the same result. Okay, so by that we can verify whether it is commutative or not. Of course we can prove it, but we are just taking this example, and whether it, if this I mean if the equality doesn't hold for this example, then it is not true in general. Okay, so we have, it's a kind of, we have come up with some counter examples. Okay, so what should we do? So you recall the formula. So if you want to compute the inner product of two complex vectors, first you take the conjugate of the vector, the x vector, and then you just transpose it, right? So taking conjugate is very important, and then you just multiply the elements of these two vectors element wise. Okay, so it goes like this. First we take the conjugate this sorry, yeah. So now I am taking this element and conjugate it. Okay, so 3 minus 2i, so it becomes 3 plus 2i. Then I am taking the first element from here as it is. We are not doing any conjugation here. So we are just simply multiplying two complex number. Similarly, I will take the second element, okay, and then conjugate it, and then take the second element from y and simply multiply it. So you keep doing that, and finally we have to sum it up. Okay, so it's very simple. I hope you can work it out. You just multiply two complex numbers here. So if you multiply these two complex numbers, you will get a complex number as an answer, which is minus 14 plus 8i. Similarly, you take the second element from x, conjugate it, which is minus 2 minus i, and then take the second element from y, and then you just multiply this together, then you will get this complex number. Again, you take the third element, conjugate it, and then take the third element from y, multiply it, so you will get this number. So what you have to do, so in a proper multiplying all these elements, you have to sum up the result, right? So we can again visualize this as if you are feeding it to the summer. It's a nice diagram. So you just sum it up all the elements, you will get an answer. So if you multiply two complex vectors in the order x and followed by y, you will get the answer minus 19 plus 13i. Okay, so the question is, will it be true if I interchange the orders of the vectors? Okay, so instead of x dot y, if you go for y dot x, what will happen? That we will take a look. So by definition, y dot x, the inner product between y and x is y conjugate transpose, which is a y Hermitian, and then x multiplied by x. Okay, so let us do that. Now in this case, again you have to take the vector from y and then conjugate the vectors and then multiply it with the vector, I mean the elements from x. So the first element from the y is, yeah, it's minus 2 plus 4, right? So if you conjugate it, this becomes minus 2 minus 4i, right? And then you simply multiply the same with the first element from x. Okay, so the first element is 3 minus 2i, and we are not taking any sort of conjugation for the elements in x. Okay, so because we have to take the conjugate of elements only in the y. So if you keep repeating this thing like we did earlier, take the second element from both the vectors and then take the third element, you will get these numbers. then you just sum it up. So this gives some number. So it's minus 19 minus 13i. So you just compare the result of the previous one, that is x dot y, and this one, that is y dot x. So what is the change? Okay, the real part remains same, but the imaginary part is actually, it's a kind of conjugate, right? So in general, y dot x is not equal to x dot y. So here the answer you could interpret as x dot y. So whatever the answer we obtained for x dot y, okay, so which is, so for x dot y we obtained the answer of, I think, minus 19. Oh, it's I have to choose a pencil. So x dot y is, in the previous example, or in the previous case, the x dot y was minus 19 plus 13i. So y dot x is simply, instead of computing it again, we can simply get the answer by taking a conjugate for this one, which is equal to, conjugate of this one is equal to minus 19 minus 13i. Okay, so now with the help of this example, now we know that, okay, now we know that x dot y is not equal to y dot x, or in other words, we say it is not commutative in general. Okay, and you can think of some examples, okay, or under which condition or for what types of vectors this x dot y becomes equal to y dot x. Okay, so you can think of such examples, and I leave it to you for your thinking. Okay. Okay, now let us, again, this is some sort of proof, which is a simple one. So there are many properties for this inner product space, right? So we have just seen that in general x dot y is equal to y dot x conjugate, right? So we considered a specific example, and then we have just noticed that it is not true for that example. Sorry, it is true for that example, right? So because x dot y is equal to y dot x conjugate, but is it always true for all the examples? Yeah, so for that we have to prove it, right? So it's the proof goes very simple. It's not a tedious one, so you can just pay attention. So you can write this y dot x whole conjugate as like this. Okay, remember I have just replaced the dot product by this y conjugate into x whole conjugate. Okay, so of course that should be transposed. Then you can expand this. Okay, so we simply take conjugate for all the elements in y, which is y1 conjugate, y2 conjugate, and yn conjugate, and then we multiply it with the respective elements from x1, x2, xn, and then we take a whole conjugate, right? So there should be a whole part, but using the properties that x dot y whole, I mean a dot b whole, ab whole conjugate equal to a conjugate b conjugate. So we have just written down like this. Now again you use the properties of the conjugate, okay, which is, after applying this, it becomes some sort of, say, y1 conjugate of conjugate and x1 conjugate. So y1 conjugate of conjugate is simply y1. So we simply shifted the conjugate from y to x. Okay, so which you could write this, you can simply interchange the elements. It's simply a product. So now you can write this as x dot y. So now we have just proven that x dot y is equal to y dot x whole conjugate. So we considered the right hand side and just shown that it is equal to the left hand side. Okay, so you could do the other way around as well, but this one is straightforward. So the proof is simple. Let us move on to the next question. So usually in real inner product space, where we are given two vectors in real space, real vector space, apart from taking this inner product, this inner product also helps us to find the angle between two vectors, right? So if I have vector x and vector y in, say, for example, R2, then computing the inner product gives me the projection of x onto y, and also it we can obtain the angle between x and y. So in the same line, we can we use the inner product in the complex space to compute the angles in the complex space or angles between two complex vectors? So there is an ambiguity, of course, we have to acknowledge, right? So we say it's not always. So the reason is, in order to compute the angle between two vectors, we go with this equation, right? So x dot y, and then the length of x and then length of y. Okay. So if it is a real x, if x comes from the real vector space, x dot y is going to be a real, and length of x and length of y is also going to be the real. So we can compute the cosine angle between x dot y because the angle is going to be in real number. So we can make sense of it, right? But in the case of complex vector space, x dot y is not always going to be a real number. For some vectors, it might turns out to be real number, but for other vectors, it turns out to be a complex number. So defining a cosine angle might gives us some gives rise to some sort of ambiguities or inconsistency in definition of angle. Okay, so some authors prefers this way as well. So you just take the real part of the result and then you just compute the angles, but it's again so there are difference of opinions about this. So you can read about the summary. Okay, so whether defining a complex angle for complex vectors in the complex vector space. Okay, so you can refer to this, which I have given a link to a paper. So if you click on it, it will lead to that link. So you just go through it if you are interested. Okay, so I will post this slide anyhow in the portal, then you can download and use it. Okay, so it's just for your information. Okay, having said that, now we are moving into another problem. So far we were able to compute the eigenvectors for the real matrices or matrices, right? So given a real matrix, you were able to find the eigenvalues for the real matrix, and also you know how to compute the eigenvectors for the real matrix. So here is an example where the matrix is actually complex, and the question is, can we find the eigenvector for this complex matrix? Of course we can. Okay, so there is no change in the procedure, so you have to follow the same procedure. So you compute the eigenvalues, and for given eigenvalue you should be able to complete the eigenvectors as you do for the real matrices. Okay, so that there are no differences at all. So in this case, we are given with the eigenvalue, so we have to compute the eigenvector. Okay, so the n denotes the null space. So you substitute lambda there and you subtract lambda, so you will end up with this matrix. So this matrix is actually, I have taken this from the lecture, so I am just going to show you how to obtain the eigenvector for this matrix for the given eigenvalue. Okay, so what do you do? So first we have to row reduce. So to do that, if you just notice, right, okay, you just notice that I have -6 here, 3 plus 3i here, so I have to make this as 0. So what should I do? So you simply multiply the first row by this complex number. Okay, so if the matrix was real, then you would have used a scalar, that is real scalar. Now it's a complex number. Okay, so you can figure this out. This is going to be 1 by 2 into 1 plus I, because this is 3 plus 3i. So what I want is -3 minus 3i. So we simply multiply this complex number with the row 1. Okay, and then you just add them together. So you will get a matrix something like this. Okay, -6, 3 minus 3. So you just work it out. So you will get this one. So now I can simply find the eigenvector by finding the x1 and x2 that belongs to the null space of a minus lambda I. So since the second row is, all the elements of the second row is 0, so we get a simple equation that is -6x1 plus 3 minus 3i into x2 is equal to 0. So now x1 and x2 are free variables, so we can put some fixed values to x1 or x2. So yeah, we can rewrite this. Let me this is the final equation that we have 2x1 is equal to 1 minus 1i into x2. So we have to put some values for x1. Let us say we put a value of x1 to be 1, then x2 you can get by moving. Okay, so everything now becomes very simple. Oh, I have to choose. Yeah. Okay, so x2 is simply, since x1 is equal to 1, I replace this by 1. So now we just move this here. Okay, 1 minus 1i. So that is what you are seeing here, 1 minus 1i. Yeah, so instead of using just I, I use this 1, which is a coding terminology, by the way. So you can ignore that 1 if you want. Yeah, so this is an eigenvector, but somehow we can rewrite this. Okay, using a complex conjugate of the denominator. So I am just enhancing it. Okay, so x2, I replace this, rewrite this x2 something like this. So you will get x2 is equal to 1 plus 1i. So the corresponding eigenvector, or the eigenvector corresponding to the eigenvalue lambda 8 is 1 and 1 plus 1i. Of course, any scalar multiple of this 1 by 1 plus i is also an eigenvector of the matrix A for the eigenvalue lambda is equal to 8. And also one question that I'm asking you right now is that whether the scalar multiple should be a real number or it could be a complex number. Okay, any complex multiple of this x is also going to be a eigenvector, or only the real multiple of this x is an eigenvector. Okay, so you just think about it. Okay, so similarly you can find the other eigenvector for the matrix A by following the same procedure. Okay, so because why am I solving this in this tutorial problem is, if you want to do eigen decomposition actually for this matrix A, so you have to find the eigenvectors first, right? So since it is a complex eigenvector, I think this example will help you to find the complex eigenvectors for any given matrix A. Okay, the procedure is going to be same. Okay, so the next problem is about the unitary matrix, and recall that we say a matrix, given matrix U, say for example, is unitary if U into U transpose or U into U Hermitian is going to be an identity matrix. Okay, so if you multiply U and U Hermitian. So in this case, we are given with the U, so we have to check whether it is unitary. So for that, we need the U transpose. Since all of them are going to be real numbers, we are just writing this as U transpose. So if you simply transpose the matrix, so you will get this one. Okay, so you just multiply U and U transpose like we do for regular numbers. Okay, so instead of the elements of the matrix being a number, here the elements of the matrix are just a functions. It doesn't matter anyhow, multiplying a matrix, the way we multiply the matrix is going to be the same. So we can just do matrix multiplication, and once if you do that, you will get this matrix. Okay, it's a very simple, cos square t plus sin square t, all these things. So you can see that after multiplying this, right, so though it looks like a big matrix, but it is not actually in fact big. So we have cos t sin t term here, we have sin t cos t term here, and therefore they become 0. Similarly, we have sin t cos t term here and cos t sin t term here. Subtract these two, becomes 0. So this term, you must have recalled this is 1 cos square theta plus sin square theta, and this term is also going to be 1. Okay, remember t can take value from 0 to pi, but we don't care about what value t takes. We simply substitute t. So we show that it is going to be it is in fact a unitary matrix. So all the elements are, it gives me an identity matrix as a result. Okay, so it's going to be 1 0 0 1. Of course, we can change the sign of something and we get the sum of the elements, and if we get the same result, then again it is a unitary matrix. Okay, so you can prove this for any given matrix U. You take U and then U Hermitian or U transpose and see whether it is an identity matrix. So if it turns out to be an identity matrix, then it is a unitary matrix, and a unitary matrix is also an orthogonal matrix. Okay, so in this case we can say it is an orthogonal matrix as well. Okay, so now we have just seen that unitary there are some properties about the unitary matrix, right? So especially they preserve the length of the vector being multiplied. So here is an applet that demonstrates. So in the previous example, in this example, you just take a look into the elements of the matrix, which is the functions cos t and sin t. And as I told you earlier, t can take value from 0 to 2 pi, and for all the values of t, it is going to be unitary. Okay, not just for t is equal to 0 or t is equal to pi. For all the values of t, it is going to be a unitary matrix. So I'm going to substitute various values of t into this matrix and going to multiply that matrix with the vector x shown here. Okay, so in the applet, the vector x is, of course, we are in R2. So the input vector to this matrix is going to be this one. So this vector is actually 1, 0. X is 1 and y is 0. So if I apply, so it's a kind of, we are doing a matrix transformation. Okay, so we are multiplying a matrix by a vector, so it transforms the vector, right? And since this is an orthogonal vector, so it is going to transform the vector somehow. Okay, so let me substitute various values of t and generate a different matrix and apply all those matrix onto this vector x and see what it does. Okay, now the t varies from 0 all the way up to 2 pi. Okay, so now we are going to use this matrix. So when I vary t, right, so I have just varied t from 0 to 0.16. So you can see that it transformed the vector x into a new location that is denoted by this red vector y. Okay, and if you look at carefully, the length of the vector is not changed. Okay, it is neither stretched nor shrink, it remains same. Okay, what is the change? The change is it just changed the direction, which means it's rotated it, right? So let me change the matrix. So for each value of t gives me a new matrix, but all of them are going to be unitary. And let's do that. Wow, see what happens. I'm just changing the value t. Now t is, let me stop, 3.14. Okay, so you know what is 3.14, it's pi. So now we are halfway, right? So all these different matrices acted on x and just transform the x into, it preserved the length of the x, but it just changed the direction, right? So if I complete this all the way up to, yeah, okay, 6 point up to 2 pi, you can see that the vector actually made one anti-clockwise rotation. Okay, so you can see that it also preserves the length of the vector. Okay, this is true. Now we have visually just demonstrated that yes, it preserves the length of the vector. What happens if we don't, if in this case it is a unitary matrix, but if I apply non-unitary matrix, say for example, I'm calling this as non-unitary, I don't know whether it is a standard way of calling it, but let us say I applied some random matrix. Okay, so let us see whether it preserves the length of the vector x being transformed. Okay, yeah. So instead of unitary matrix, I am going to consider some matrix composed of these elements. Okay, so cos term is there, tan term is there. Of course, you can show that if you multiply this A by A transpose, you won't get a identity matrix. So we can say it is not a unitary matrix. Okay, so now whether it preserves the length of the vector x, if I apply on the vector x, see for no values of x, or there may be some values of x, but in general, okay, it doesn't seem to preserve the length of the vector x for all the values of t, right? So we can say for some values of, we might say for some values of t it might be unitary, but for other values of t it is not going to be unitary. So the function cos t minus tan t cos t is not unitary in general, but for the previous case where we have cos t minus sin t and cos t, it is unitary in general for all values of t. Okay, and you see for non-unitary matrix transformation, the length of the vector is not preserved when it gets transformed. Okay, so now I hope that you get some idea about these unitary matrices and what do we mean by length is preserved, all these things. Okay, so even if you don't get it, it's all right, you just work out few more examples, you will figure this out on your own. And yeah, there are a few more concepts that about solving singular value decomposition, all these things, but since you know how to compute the eigenvectors of a matrix, and doing the same for singular value decomposition is not going to be that much difficult. Okay, so I didn't come up with any examples to do that, but we will solve such problems in like solve with instructor session. Okay, and also you have few problems in activity and practice questions, so you do solve them, and if you have any doubts, let us discuss all such doubts in the open session. Okay, thanks for watching this tutorial, and if you have any doubts, please note it down. Hoping to see you all in the live session. Bye bye.